Hi everybody, this is lecture 10 on atomic structure and properties of matter. Okay, so let's get into it. So let's start with a quote from Richard Feynman. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. Okay, so that kind of sums up the atomic hypothesis. Okay, so some characteristics of atoms. They're incredibly tiny. They're numerous. They're all around us. They're perpetually in motion. They're always in motion, and they're ageless. Okay, so this is the hypothesis. Some of these are true, and some of them are not. Let's go through it. The atomic hypothesis dates back to the 5th century BC. The term atom means indivisible. Aristotle believed that all matter is composed of 4 elements: earth, air, fire, and water. And this idea persisted for more than 2,000 years, which we know that's not true. Atoms were first proposed by John Dalton in the early 1800s and discovered by Robert Brown in 1827. And this was explained by Albert Einstein in 1905 using Brownian motion. So Brownian motion is a thing that Albert Einstein talked about, which is the bouncing around of tiny particles in a fluid due to the random motion of atoms. He was to explain it using the atomic hypothesis. Okay, there's a couple of points through history where the atomic hypothesis came to be. One of the early ones is this Thomson model, where the negatively charged electrons, let's just read it here. Thomson's plum pudding model was disproved in 1909 by one of his former students, Rutherford, who discovered that most of the mass positive charge of an atom is concentrated in a very small fraction of its volume. So that's this one. The Thomson model, I can't remember if it's the blue are positive and the red, or the salmon, is negative, but the charges were separated, and small particles in blue were surrounded by entirely of the particles of the other type. And Rutherford showed this isn't true. It's not fruit in a plum pudding that's throughout space. Rutherford found that the atoms are mostly empty space using the gold foil experiment. So this gives us the picture of a tiny nucleus in the center surrounded by tiny electrons and mostly empty space. Okay, so we're talking about the nucleus, which is this red thing here. It's a very dense nucleus in the center surrounded by orbiting electrons. The nucleus consists of nucleons, which are protons and neutrons, and they're made of quarks, which we're not going to worry about. The nucleus is positively charged because the protons are positive and the neutrons are uncharged or neutral. And it's held together by the strong force. So it's this tiny thing in the center of an atom, and the atom is surrounded by an electron cloud, but it's super tiny in the middle. It's positively charged. The electrons, they surround the nucleus, which is a tiny thing in the center, and they surround it. In the plum pudding model, is the negative electrons were these tiny plums surrounded in the positive plum pudding. That was wrong. That wasn't right. Instead, we have it moved towards the solar system model, where the nucleus is made of protons. It's right in the and neutrons in the middle, surrounded by a cloud of electrons orbiting the nucleus. Okay, and then as they continued to make progress, they understood that these orbits of the electron were, we can think of them in terms of shells in the Bohr model of the atom. So in the Bohr model, the electrons orbit the nucleus in circular orbits denoted by n. Only a specific number of electrons are allowed in each orbit, which will help build out the periodic table. And each orbit has a specific quantized amount of energy and angular momentum assigned to it. We don't need to worry about that. We'll look at the periodic table and understand what that means. Okay, and there's these different transitions between the different shells. So a transition from a low shell to a high shell absorbs energy. A transition from a high shell to a low shell releases energy. And the energy is absorbed and released by emitting or absorbing photons of light. Okay. So in quantum mechanics, we can figure out what those shells actually are by, this is really complicated, there's a bunch of math behind it, but we can build up these shells of the electrons flying around the atom using this math. And here's some pictures of the complicated probability distributions of the shells, which we're not going to worry about. What we do need to worry about is, I'm going to skip ahead quickly to, here we go, the periodic table. The periodic table tells us about the electronic structure of atoms and how that relates to how how elements interact with each other and form compounds. So all of these models of the atom and the complex calculations of the electron clouds build up to this periodic table of the elements, where we understand these are the noble gases, and these are very reactive, these are your metals, these are super reactive over here. And as we get higher and higher, we get into synthetic and radioactive elements, which is not to do with the electron structure, but the fact that this is how we started to discover new and new elements that were radioactive. Okay, so let's go back. What is an element? An element is a substance that's composed of only one type of atom, so not a compound with multiple atoms, but just one type. So an example, gold, oxygen, carbon, which in the periodic table, here is gold, where's gold? Gold is right here, carbon is right here, oxygen's right here. So those are elements. Okay, hydrogen is the lightest element and also the most abundant, so that's up here. That's got 1 proton, 0 neutrons. There's 118 elements have been identified, so let's see, 118. So if we count all the elements have been all the way from hydrogen to oganesson, that's 118 total elements have been discovered. They're all listed here on the periodic table. 90 are found in nature, and the rest are produced in labs. So most of these, and up to 90 of them, are produced naturally, and a lot of these higher numbers are produced in a lab. Okay, and living things are mostly composed of carbon, oxygen, hydrogen, nitrogen, and calcium. Okay, so these are these lighter elements up here. Okay, so the periodic table was created by this guy Mendeleev, first published in 1869. It only had about 60 elements, but that's okay. He was able to start putting together patterns of how atoms and their chemical properties started to fit together. Okay, and this is the periodic table. This is very important. Okay, so if we look at the periodic table and we look at the relative sizes of atoms, if you start from lightest elements have the smallest atoms, and heavier elements as we go down have the biggest atoms. And if we start on the left, we get bigger, and we go to the right, things get smaller. So it's high up, lighter elements are small, heavier elements are big, things on the left are big, things on the right are small. Okay. All right, ions and isotopes. So in a neutral atom, the number of protons in the nucleus matches the number of electrons around the nucleus, but not necessarily neutrons. So an isotope is an atom with the same element with a different number of neutrons. So on the periodic table, we'll take, say, zirconium. That always has 40 protons in the nucleus and 40 electrons if it's an atom around the nucleus. But the number of neutrons there may be several values of neutrons. Those different values of neutrons in a particular atom are the different isotopes of zirconium. Okay, an ion is a charged atom. So sometimes atoms lose an electron and they can become charged, positively charged. So that would be a positive ion. And if something has an excess of electrons, that's a negative ion. And that an ion is a charged particle that has to do with if it has extra electrons or a deficit of electrons compared to the proton number. Okay, let's do some questions. The atomic number of an element matches the number of protons in the nucleus. Because if we look at the periodic table, each element here is got a proton number. So potassium is 19 protons. Silicon is 14 protons. We don't care how many neutrons. So protons. So A. Oh, of course. Electrons in a neutral atom. So since the protons and the electrons have to be matched for it to be a neutral atom, then protons and electrons are the same in a neutral atom. So A and B are both true. But I would emphasize the important part is the element is determined by the proton number. Okay. A new atomic number of an element matches the number. Oh, I did that one. A nucleus with an atomic number of 44 and a mass number of 100 must have. So an atomic number is the number of protons. So it's got to have 44 protons. If it has a mass number of 100, that's 100 total protons plus neutrons in the nucleus. So that means there needs to be 56 neutrons in the nucleus. Okay. When atoms have a different elements bond to another, they make compounds. So that's atom and atom together. It can be multiple atoms coming together to form a compound. A mixture is when you take two compounds or elements and you just mix them up. They don't actually chemically bond. Okay, so some good examples of compound: table salt, water is a good example. A mixture would be like a mixture of sand and nails. So there's still nails, there's still sand, but it's just a mixture. Okay, so here's some examples of molecules. We got O2, oxygen. We've got NH4, I'm not sure what that's called. CH4, and H2O, that's water. Yeah, there's so many millions, there's basically an infinite number of these combinations. So these are some examples of molecules. And a chemical reaction is when we change from one type of compound to another. This can require energy or release energy, but it's when we change between types of molecules through a chemical reaction. Well, that's a chemical reaction. Okay, antimatter. Antimatter is, well, it's this mysterious thing throughout the universe where the proton, so for our regular matter, the nucleus is positively charged and the electrons are negatively charged. In antimatter, the nucleus is negatively charged with antiprotons, and the electrons are positrons on the outside. Everything's exactly the same, and when two matter and antimatter ever meet, they annihilate each other and just leave photons behind. They always annihilate each other. Okay. Dark matter. Dark matter, we've talked about dark matter before. It's a mysterious thing. We don't really know what it is. We know it has to be there because of galaxy rotation curves. We don't know what that is. I'm not going to speculate. Okay, let's do some questions. Brownian motion has to do with the random motions of atoms and molecules. That's what it has to do. Okay. All right. And Einstein used that to determine that fluids were made up of atoms and smaller constituents. It is correct to say that atoms make up your body. It is correct to say that atoms that make up your body were formed in ancient stars. That sounds right. Were previously a part of your neighbor's bodies. Yeah, we do. The atoms are always moving through the environment, including ourselves, are in motion at all times. That's true. So all of these, it sounds like. Okay. Compared with the wavelength of visible light, atoms are about the same size, smaller, larger, fuzzier. I think smaller. Visible light's quite large. Which of the following has the smallest mass? Proton, neutron, electron. So a proton and neutron have almost the same mass. The electron is much lighter, much less massive. Except for slight differences, all have about the same mass. That's wrong. The electron's much lighter. Okay. The reason you don't fall between the atoms and the floor you stand on involves, well, all the atoms are mostly empty space. Why don't we just fall right through? That doesn't happen because of electrical forces. Okay. An element is a substance consisting of atoms of the same kind. Okay, it sounds right. Atoms are molecules of the same kind. Well, not molecules. Only protons? No, not only protons. We've got protons, neutrons, and electrons. Protons and electrons in balance, not necessarily. It could be an ion. So it sounds like atoms of the same kind is the best answer. Okay. The classic periodic table has 4 legs. That makes no sense. That's ridiculous. Lists the known elements. That sounds right. Is now outmoded and has been replaced by modeling programs. None of the above. It sounds like it lists the known elements. Yeah. Investigation of atoms sequenced along each horizontal row period of the periodic table shows that atoms decrease in, well, not mass, as we go across. Let's go up to the periodic table. Went too far. Here. In fact, this one is better. Right, as we go down and across this way, as we go from the left side to the right side, atoms get smaller. Okay, so if we go to that question, where are we? Okay, along each horizontal row, the period shows that atoms decrease in, so as we go across the row, they should decrease in size. Increase in mass, decrease in size. Okay. If you add or subtract a proton to or from the nucleus of an atom, you produce a completely different atom. That's true. An isotope, no, that's if you add or subtract a neutron. An ion, no, that's if you take or add an electron. It's got to be a completely different atom. Okay. The atomic number of an atom is defined in terms of its number of, we know, protons. Not neutrons, that's different isotopes. Protons and neutrons determines the mass number. Protons, neutrons, and electron is the whole atom itself. What we define each element by, or atom by protons. Okay. The size of an atom is mostly determined by the space occupied by its electrons. The nucleus is tiny. The protons and neutrons are in the nucleus and they're tiny. The electrons are that big cloud around the outside. That determines how big the atom is. Okay. Which of these elements has atoms of the greatest mass? Well, we can look at the periodic table to do this, but we know uranium is the heaviest. If we look at the periodic table, we can find that as the highest atomic number. Okay, which of these elements has atoms with the greatest number of electrons? Well, it's going to be uranium again, because it has the most number of protons. If it's a neutral atom, it must have the largest number of electrons. It's got to be uranium. Molecules are composed of atoms, electrons and protons, and neutrons, so that's not a good answer. Atomic nuclei and orbiting electrons, that sounds like an atom. Particles larger than atoms, that sounds right. But I think the best answer is molecules are composed of particles. So a molecule is a particle that's made up of many atoms bonded together. So molecules are composed of atoms, I think, is the best answer. Okay. Atoms combine to form molecules by way of not nuclear forces, because it's the nuclear forces is inside the nucleus. We want electric forces. Electric repulsion, it's playing a part. Shared or exchanged electrons, that sounds the best answer. Neutron attractions. Neutrons don't attract one another, so we got shared or exchanged electrons sounds best. Okay. A compound is composed of different kinds of atoms mixed together, not mixed. Moving at the same average speed, that's kind of a weird answer. Indefinite proportions, that sounds good. In the gaseous form. These are kind of weird answers to me, but I think the third one is the best. Okay, so it's like H2O, always 2 hydrogen atoms to 1 oxygen atom. The atoms and isotopes of a particular element have different numbers of neutrons. So electrons and protons are in balance if it's not an ion. The proton determines the element, and the number of neutrons determines the isotope. So neutrons. Isotopes of a given element differ in not atomic number, because that's the number of protons, not electron number, because that should match the number of protons. Mass number sounds right, because that's protons plus neutrons. They're placed in the periodic table. No, they're the same spot. Isotopes are in the same place in the periodic table, so it's mass number. Okay. The shell model of the atom views electrons as occupying, well, shells. Three-dimensional orbitals. Shells sounds right. Three-dimensional orbitals. That sounds even better. Circular elliptical orbits. I don't think so. Standing waves. That sounds like the best. Oh, shells is the best answer. Okay, that's almost redundant. The shell model has us viewing electrons as occupying shells. Okay. If 1 gram of antimatter meets with 4 grams of matter, the energy released would correspond to the energy equivalent of, we've got when matter and antimatter meet, they annihilate. Well, 1 gram of antimatter is going to annihilate 1 gram of matter. That's 2 grams total. So the energy equivalent would be 2 grams. Okay. And that's it for today's lecture. And see you guys next time.